All right, we're going to talk about Gauss's law today. Okay, so let me tell you what this thing is about. Okay, so let's say we have a bunch of charges here in this room. What do these charges do?
They interact with other charges.
Okay, they interact with other charges. What does this charge do? It produces fields. How does it interact? It produces fields. Okay, so let's say I want to calculate the electric field here. What does this fellow do? He produces an electric field there, and we'll call this Q1, Q2, Q3, Q4, Q5. The magnitude of the electric field is in that direction, and the magnitude of the electric field is K Q1 divided by R1 squared. What does this guy do? He does the same thing. He produces E2 in that direction. E3. These are all vectors, by the way. E4 and E5. So what is the total field there?
The net sum.
It's the sum of those 5 vectors, okay? And that's the superposition principle. All right? So I found the electric field here. Now I want to know the electric field here. In fact, what I really want is to know the electric field everywhere in this room. So I've added these 5 vectors, no big deal, I'm not tired yet. I'm going to find the electric field there. Not tired yet, here, 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 I'm tired now. I need a better way to find the electric field. And that's what this chapter is about. Okay? Now, for this general situation, that method won't work. So the method I'm going to tell you to calculate the electric field everywhere will work for a symmetric charge distribution. So here's an example. It'll work for that. Okay. So this is a parallel plate capacitor that's been charged, and the electric field here is constant. Sigma is the charge density, is sigma by epsilon. Okay. Why do we need to know the electric field everywhere in this room?
To determine where particles would go.
That's right. You guys talked about the inkjet printer. What did you do to the inkjet printer? You gave it a negative charge and shot it. And then when it shoots, if you know the electric field, you can calculate the trajectory exactly, or rather. And you know where it'll hit the paper. So that's what it's about. What we want to know is the electric field everywhere. All right, so Mr. Gauss, he was a very, very smart fellow. And he gave us a law to calculate the electric fields in symmetric situations. So we'll build up the technology for that and see how to use it. We'll see how to use the Gauss's law. It's convenient for calculating electric fields of highly symmetric charge distributions. Okay? So here's a charge distribution. So to be able to use Gauss's law, you need to have uniform charge density, and this needs to be symmetric. So for instance, if you had this was a plastic sheet, you smear it with charges uniformly, and this was an infinite sheet, I could tell you the electric field in this half of the universe and this half of the universe. You put a kink on it, and you're out of luck now. Okay? You take a wire long straight wire, put a uniform charge, I can tell you the electric field everywhere in the universe. You put a kink on it. Okay. All right, so that's what we mean by highly charged symmetric charge distribution, and we'll calculate the electric field. Okay. So Gauss's law relates electric fields at a point on a closed Gaussian surface, okay, to the net charge enclosed within the surface. Okay, so you can draw any imaginary surface you want. So the theorem relates the electric field on the surface to the charges inside. And that'll help us calculate the electric field in symmetric situations, okay? So I'm just introducing terminology. What's our goal today?
To be able to describe the field at any point.
That's right, define the field in this room, okay? All right. Given a chart distribution. Yeah. So first we'll start off with material flux, okay? So what we want to do is, so imagine this is a river, and this is the velocity field. What do you think that's telling you?
It's velocity at any point.
So yeah, that's telling you the velocity of the water at any point, and you can see from the direction, the water is flowing at 10 meters per second at every point in the river. Okay? Okay, let me answer this. Hello? Sorry about that. All right, so this is the flowing river. And what we want to know is how many gallons of water are passing through this per second. And that's given by the flux, material flux, and it is A, the area of this ring, times the velocity of the water at that point. Okay, so you see A, area is length square, and velocity is length over time. So this is volume over time. So it tells you how many gallons are flowing per second. Okay, so this is material flux. What if this ring was like this? Zero. Nothing is flowing through. Okay, so it depends on the angle. So what we'll do is we'll define an area vector. And what does the area vector mean? The magnitude of the area vector is just the magnitude of the area, and its direction is perpendicular to the area. So why do we define that? Because now we can write the volume flux as velocity vector dot A. Okay? Let's see if this works. Let's make the area vector point in this direction. The velocity vector is in this direction, and V dot A is 0 for this guy, and the flux is 0. Okay? If for this guy, area vector and velocity vector are parallel to each other, the flux is just V times A, which is that. Okay, so that's why we define that. Everybody understand that? So it works for both limits. All right. So the flux is the volume of water flowing through that area. Okay? Well, now we're going to do the same thing with electric fields. Okay? So what we want to know is the following. So here's electric fields in this region. What we want to know is what is the Do you guys remember how did we choose to draw stronger fields?
More lines.
More lines.
Stronger field.
More lines for stronger fields. Okay, so now we're going to ask, just like in the previous case, how much volume was flowing. We'll ask how many lines are going through this area. Okay? And that's what we'll call electric flux. The number of lines will tell us the electric flux. So we just defined the electric flux very similar to that. Electric flux will be defined, flux is denoted by phi, subscript E telling you that it's an electric flux. We are preparing you for a couple of chapters later. We'll talk about magnetic flux later. So that B will indicate magnetic field. So electric flux is E dot area. Okay? And that tells you the number of lines going through this area. So for instance, if I had an area like this, the area vector would be like that. And what is the number of lines going through that area? 0. Okay. All right. Now we have the technology for Gauss's law. Okay. Anyway, so the electric flux through an area is E dot A. Okay. And you can see that the flux through this area, even though this is a larger area, is the same as the flux through this area, which is a smaller area. Okay. All right. Now we'll, so this is a three-dimensional surface. It's an enclosed surface. Now we'll agree to the following rule. If there's a net flux going out of the volume, that's considered positive. If lines are going into the surface, that's negative flux. And, so the area vector will always be drawn outside the basketball. So if you have a basketball, the area vectors always point outside the basketball, not inside the basketball. Okay? So here's the basketball. For this surface, area vector is pointing like this. For this element, area vector is pointing like that. Okay. So the flux through this element is the area vector dotted with the electric field at that point. Okay. So area vector dotted with the electric field vector. And then we'll sum over all the elements. Okay. Now in the limit these area elements are small, this just turns into a surface integral. Okay. This is just a surface integral, and if it's an enclosed surface, we'll call this, you guys might have seen this symbol. We'll write that. If you write a little circle on that integral, that means you're doing a surface integral over an enclosed surface. You don't have to do a surface integral over an enclosed surface. You can do it on an open surface. Okay? But if you're doing over an enclosed surface, we convey that fact by writing a little circle. What Gauss tells us is this, for an enclosed surface, dA, Gauss was able to tell us that this is equal to the charge inside divided by epsilon. The total charge inside divided by epsilon. And that's Gauss's law. Okay. So here's the thing. Okay, I'll put a charge here. So here's a fairly neat thing about this law. Okay, I'll draw this surface. Okay. I'll do this surface integral for this surface. I'll get a number. And that number is equal to the charge inside divided by epsilon, and that's the charge inside. Let me draw another surface. I do the surface integral on that. What's the value of the surface integral on that?
Q inside.
Same thing. All right. All right. So that's a neat thing about that. All right. So flux is positive when lines project outward from the surface. Okay. And if the net flux is going inward, then the flux is negative. So you already see that if the flux is positive, the charge inside, net charge inside is positive. If the net flux is negative, the net charge inside is negative. And that makes sense. We already know for a single charge how things look. So for a positive charge, you draw a sphere, the electric field lines, you'll get a positive flux. And for a negative charge, you'll get a negative flux. So maybe Gauss was right. Okay? All right. I can show you a little. Okay, so here is a charge, and see it's creating a field in all directions, and I guess I can't draw a Gaussian surface, but what this is showing you is the electric potential. Yeah. Oh well. So you can draw a Gaussian surface, calculate the flux on the Gaussian surface. Oops. Draw a Gaussian surface, calculate the flux on that surface, and that'll equal the charge inside. Okay. So for a closed surface, the surface integral is denoted by that. Okay. And that's the net flux coming out of the surface. Okay. So if there were positive charge, net positive charge inside the surface, there'll be more lines coming in than going in, coming out than going in. Okay. If more lines are leaving the surface, then the net flux is positive. Okay. So here's an example. Okay. So let's say there's a uniform electric field in this room. Okay, and we've just used a cube to simplify things. Okay, the flux through this thing, this face will be the electric field times the area of this face. What will be the flux through this face? 0. So through those 4 faces, it'll be 0. And the flux through that guy will be negative. The same, and the value will be the same as that. So you just, using Gauss's law, you just concluded, yeah, well, we haven't told you the Gauss law. Actually, I've told you the Gauss's law here. The net flux is equal to charge inside divided by epsilon naught. So what can you conclude? If you have a uniform field in any region, you can't have a charge anywhere there. Okay? So the only way to have a uniform field is, this is one way to have a uniform field. And this is a parallel plate capacitor. You can smear this wall with positive charges and smear that wall with negative charges, and you can have a uniform field here. Soon as you put a charge anywhere in this room, you put this charge, and that'll ruin the uniformity of the field. Okay. All right. So that's what this is showing. So the net flux through this thing is 0. So in a uniform field, the net flux through that cube is 0. Now you can just move the cube around anywhere and conclude that there's no charge anywhere in this room. Okay? So here's Gauss's law. Okay. The flux through an enclosed surface is equal to the charge inside the surface divided by epsilon naught. Okay. Epsilon naught is permittivity of free space, and that's the value. Okay. And you guys might know that the Coulomb's constant is related to the permittivity of free space, like that. Okay. All right, so you see, so here's a bunch of charges, and these are all imaginary Gaussian surface. So the net flux through this guy will be 0. The net flux through this surface is negative. The flux through this surface is positive. The net flux, and if the charges are equal, the net flux through this surface is 0. Okay? The net flux through this surface is 0, and so on. Okay? Okay, so now what we'll do is, what was the electric field due to this charge Q at this point? What is the electric field? R is the distance. Let's say R is this distance. What is the strength of this electric field at that point? KQ by R squared. Okay? And if Q is positive, that's the direction. Okay? So that was Coulomb's law. Well, that was the electric field of a point charge. So we'll show that to you using Gauss's law. So essentially, we're going to kill a fly with a hammer. Okay? So we're going to use a. All right. So here's the point charge. We draw a basketball around the point charge. Okay. And the electric field from the symmetry of the situation is always pointing perpendicular to the basketball. And it's pointing outside. Okay, that's positive. So the flux is easy to calculate. This surface integral is easy to calculate. So we'll always consider situations where the surface integral is actually very easy to calculate. Okay? So if this guy is at the center of the circle, there's the electric field, the strengths are all the same, and they're all pointing parallel to the area. So this surface integral just becomes E dot dA. E is constant and the same on all points of the surface. dA. What is that telling you? What is that?
Oh, it's a sphere?
Yeah, so it's telling you add up all these area elements on the surface of a sphere. That's the surface area of the sphere. And what's the surface area of the sphere? 4 pi r squared. And that's equal to the charge inside divided by epsilon. So the electric field is Q divided by 1 over 4 pi r epsilon naught divided by r squared. Okay. And that was the electric field of a point charge. So what we did was, so when we are given a new law, the first thing you want to do is check in the simple case where you know the answer. And that's all we did. So we checked that law for the simple case where we knew what the answer was. And now now we have confidence in the law. Now we're going to use it in situations where we don't know the answer. Okay? And we can calculate the electric field. And how would you be totally confident that that was right? You'd have to experimentally check it. Okay? So that's how science would work. Okay.
Something went wrong. Please try again.
All right. Now I'm just going to give you predictions of these of Gauss's law. Okay. Now I'm going to sort of give you the punchlines. Okay. So this is a styrofoam sphere. Okay. And we're going to smear this uniformly with charges, positive charges. Okay, in a little bit you'll learn that if this was a metal sphere and you put a bunch of charges, do you guys know what will happen?
It's going to equalize with the metal and sphere.
if you put a bunch of extra charges on the metal sphere, they'll all come to the surface. Okay? So for a styrofoam, you can put it all throughout the volume. So you have to have an insulator. Okay. So the charges are all over. And what you'll find is using Gauss's law, you can draw a Gaussian surface, calculate the electric field, and the electric field just depends on the charge inside. So if you're drawing a sphere near the center of the sphere, in the limit the charge inside goes to 0, so the electric field at the center is 0. Okay. Now you've sort of seen this situation before. Okay. So this is very similar to, this is the Earth. What is the acceleration due to gravity on you there?
9.8.
Yeah, and so the gravitational force on you is mg. At the center of the Earth, the gravitational acceleration is 0. Okay, so Mr. Newton, all right, so the electric field at the center is 0, and as you travel away from the center, the strength of the electric field gets stronger and stronger, and then the electric field on the surface is the maximum. The strength of the electric field at the surface is the maximum. That's what this is saying. And then once you are outside the sphere, the electric field strength starts falling off. So there's the electric field strength, and the further out you are, the smaller the electric field strength gets. And it actually falls off as 1 over r squared. So here's another neat fact. Once you're outside the sphere, the electric field here is as if this was a point charge. Okay? And you've seen this again before. So here's the Earth, and if you're in the International Space Station, you're going around the Earth like that. All right, and you blindfold yourself and somebody turns this into a black hole, you won't even know the difference. Okay, if this became a point object, the gravitational field will be the same, just like that. If this became a point charge, the field outside is the same. Okay. All right, so the field outside is as if it was a point charge, and the field inside increases linearly from the center. Okay, and A is the radius of the sphere. You guys understanding this? Go ahead.
Is this just a observation of a charged item? So for example, when A is 0, as in you're in the exact center, the electric field experienced is 0 because it's evenly distributed all around you.
Right. So if it was not symmetric, this would not be true. What we're saying is not true.
So if this was an actual question on paper, they would say, given 2 millimeters within a marble that's fully charged, what electric field do you expect to experience? Okay.
Okay. You take an insulating sheet, a plastic sheet, and smear it evenly with positive charges or negative charges. What you'll find is the electric field is sigma by 2 epsilon naught. So this has to be an infinite sheet. You're smearing it evenly with charges. And sigma, what is sigma?
That's the surface area.
That's the surface charge density. What does that mean?
It's Q over A.
I'm sorry?
It's Q over A.
Yeah, Q over A. How much charge there is per meter square. Okay? So here's a wall that's infinitely large, and you're every meter square, you're spraying that much charge. And then you ask what is the field, and the field strength here is sigma by 2 epsilon naught. And on the other side, the field strength is the same, and it's pointing in the other direction. Do you notice anything strange about this expression?
Doesn't matter how far away you are from the plane.
Exactly. There's no distance information. Okay? So here's the plane. The electric field 2 millimeters from here is sigma by 2 epsilon naught. In that galaxy, it's sigma by 2 epsilon naught. It's sigma by 2 epsilon naught in this half of the universe, and sigma by 2 epsilon naught in this half of the universe. Very strange.
That's crazy.
That is crazy. Okay, you can say that again, yeah. So, but that's a fact. All right. So what's going on? Well, close by, only these guys, these charges have the greatest effect. These charges have very little effect. And the further out you go, the more there are more and more charges that come in play. And so, okay. So that's what's going on. But very interesting result. Okay. So, I didn't go into the details, but again, so now we're going to take an infinitely long plastic rod and smear it evenly with charges. That charge distribution is characterized by lambda. Lambda is the linear charge density, and what does that mean? What does lambda mean?
That's the line charge density.
Yes, so that tells you how much charge there is per meter of that rod. Yeah? And you would use the Gauss's law. This is the imaginary surface you would draw. Okay, concentric with that. And all right, I'll do one derivation. Just so. Yeah. What does Mr. Gauss say? The flux through that surface, which is the surface integral dA, is equal to charge inside divided by epsilon. Okay. Remember I told you we do this surface integral only for very symmetric situations where we really don't have to actually do the surface integral. Okay. So this cylinder is concentric with that. From the symmetry of the argument, if there is an electric field, it should point perpendicular to the line. If this cylinder is concentric with that, the magnitude of this will be equal everywhere. Okay? All right, so what is this integral? What is the flux through this surface?
Q in over, or charge in over,
No, what is the flux through this? Flux through just this, the top of the cylinder?
0.
0. What is the flux through the bottom of the cylinder? 0. So there is only flux through this side face. Okay, and so this integral is, and remember the electric field is constant, so it comes out. And the electric field and that were parallel to each other, so it's EdA. So it's just this surface, the area of that surface, the area of this fella. What is the area of this face of the cylinder? It's the area of the rectangle. 2 pi r times h. Okay. So E times 2 pi r times L. Okay. And Mr. Gauss tells us that's the charge inside divided by epsilon naught. Well, what is the charge inside? The charge inside is the charge on that rod. Per meter, that's the charge. And there's an L length of charge. So the charge inside is lambda times L over epsilon naught. The electric field is lambda by 2 pi epsilon naught divided by r. Okay, well, this 2 pi is messing things up. Well, so let's fix that. We'll do 2 lambda divided by 1 over 4 pi epsilon naught divided by r. This guy is k. Okay. So the electric field from an infinitely long charge, which is uniformly smeared with charges, points radially outwards, and its strength falls off as 1 over r. So what you have seen is 3 situations. From a point charge, the electric field falls off as r squared. From an infinitely long charge, the electric field falls off as 1 over r. Okay? See, the more and more charges you're putting, the slower the electric field falls off. Now, then we did the following. We took an infinite sheet and the electric field.
Just doesn't fall.
There you go. All right. So now we want to know the following. Okay. So let's say we have a uniform electric field in this region. Do you guys remember how to do this? How would I create a uniform electric field in this room?
You would smear 1/2 positive and smear the
That's
sun.
right. Okay, so we will go stay inside a parallel plate capacitor, which you'll learn about 2 chapters from now. But okay, so we'll smear this wall with positive charges and this wall with negative charges. And what I'm drawing you is the electric field everywhere in this room is going to point in that direction, and the magnitude is, these are the field lines I've drawn, and the magnitude is the same. Okay. Now what we're going to do is we're going to go to the store and buy a piece of metal, okay, and put it there like that. Okay. And what you'll find is, okay, if you put a piece of metal within 10 to the minus 15 seconds or something like that, the field inside goes to 0. So inside a metal, the field is 0 in static equilibrium. Okay, so what's going on? What is a metal? Yeah. Why is it a conductor? It's a bunch of free electrons. How heavy are electrons?
None, basically.
Yeah, very light. You put an electric field and they respond instantly. Okay. So we put this piece of metal in there. What will happen is the electric field was there, the electrons move in the opposite direction, a whole bunch of electrons will collect here. This side became positive, and till when does this happen?
Almost instantly.
Till what time does it happen? This induced field is canceling the external field. And now the field has gone to 0 and the electrons don't have to move anymore. So that rearrangement happened in the blink of an eye, in 10 to the minus 15 seconds. So you take a piece of metal, put it in an electric field, charges will rearrange such that the electric field inside the metal is 0, goes to 0. Okay. So what has this metal done to you? It has shielded you from an external electric field. And it doesn't need to be a solid piece of metal. It can be a metal box. It'll do the same thing. Okay. So this,
Is that stating there's no, for the metal box example,
Mhm.
is that saying there's no electric field inside that box?
yeah, so the external field got shielded. You can have a field inside if you have a bunch of charges in your pocket. Okay.
And how is that different from acting as a insulator?
What do you mean? How is? Oh, if this was a wooden box, this field would go right through.
Because it will interact with the wood box.
I'm sorry? The wood box doesn't have free charges to induce a canceling electric field.
So the electric field wouldn't interact with it on its way through, it would just interact with the air inside, right?
The electric field is not interacting. The electric field is influencing free moving charges.
Okay.
And the,
And
All right.
since there is no free moving charge.
right.
Okay.
So let me do it in stages. Okay. So here's an electric field. And I'm going to do it for a solid first. And then, so what are we going to do? We're going to go buy a solid piece of copper. Okay, so here's this electric field. What does copper have? It's got a bunch of free electrons. And this feels a force in that direction, and a whole bunch of them will collect over here. What happened to this end? Well, a bunch of electrons ran there, so this end became positive. So in effect, these atoms lost the electrons, which ended up on the other side. Well, what do these guys do? They create an induced electric field in this direction. And how strong is this induced electric field? Its strength is exactly equal to this field, and it's canceling that. So, and how long did it take for all that to happen?
10 minus
15 seconds. It took me 3 minutes to tell you about it, but then it happened that fast. Well, this can't happen in a piece of wood because there's no free electrons in a piece of wood, that's all. So in a piece of wood, that electric field will penetrate. And the same thing will happen and the same thing will happen if you have a box, metal box. You are shielded from the external fields. You won't get any external field. Well, why do we care about this? You go into a building that has a lot of metal in it. Okay, so how fast did the field go to zero?
10 to the minus 15.
Okay. You guys know what is the frequency this thing works at? Gigahertz. 10 to the power 12. 10 to the minus 15 is, 10 to the 15 is very much faster than this guy. So as far as this, the signal on this, the electric field in here is concerned, that's static. A metal shield will prevent you from getting a signal, cell phone signal inside. What kind of electric field causes lightning?
A negative atmosphere.
The electric field strength needs to be 3 million volts per meter to cause lightning. Okay? Look at this. There's the metal cage. This electric field outside was causing lightning, but this person is shielded from that electric field. Okay? So in a lightning storm, well, our car's still made of metal body. What's that?
Yeah, not the same metal, but yeah.
Okay. So that's one of the safer places to be. So you want to go inside your car, in the garage, go sit in your car.
It's that principle that's protecting you from being struck by lightning.
Yeah.
So
The
your
reason
car would
why-
get shocked, but not you.
Mm-hmm.
Yeah, the reason why if a power line ever goes down on your car, you stay in your car.
Mm-hmm. All right, so a cage, like the name suggests, is protecting you. So you got a tiger running around outside. You want to be inside the cage. All right, so I'm just going to give you a bunch of results now. Okay, charge on the surface. Okay, so this is in a static situation. When you want to pass a current in a metal, you have to establish an electric field, but that's a dynamic situation, so that's a different situation. Okay, you connect a battery, and you can establish a electric field inside a metal. Okay, and the charges will respond to that. But what we're considering is a static situation. You have a piece of metal. I'm just going to throw a bunch of charges there, and they redistribute on the piece of metal, and they'll all go on the surface. Okay. So it's electric field inside. And what is the driving principle? The charges redistribute such that they want to have electric field 0 inside. What happens if the electric field is not 0?
The electrons can move.
Yeah, the free charges will move, and they'll move such till there's no force on them, and the electric field is 0 inside. Okay. All right. All charges on a conductor in an electrostatic equilibrium reside on the outer surface. So even if you have a hollow metal piece, you won't have any charges there. Okay. Well, so now let's try and mess with that. So here's a piece of metal. What I'm going to do is I'm going to put a positive charge here. What is it that you want? The driving principle is what you want is a 0 electric field here. Okay? So you do whatever it takes to make a 0 electric field. Well, this guy is producing an electric field like that. Now you gotta cancel this electric field. So what ends up happening is a bunch of negative charges collect here. Not a bunch, but I'll tell you in a second. If this was 10 coulombs, 10 coulombs of negative charge will collect here, make this 0. Okay. And so the electric field will be 0 here, and it'll be 0. And so this will become positively charged. Okay. So what we have done is, here was a hollow sphere. If this was a charge, let's say Q, minus Q will collect here, and plus Q will collect here. Okay, and so you will see field outside due to this guy. Well, these guys are producing that, but that's because of this guy. The field inside here is 0 because this positive charge and these negative charges produce a field of 0. Now what ends up happening is, you'll see in one of the problems, if this was a spherical surface, these charges distribute evenly no matter where this charge is. So what is lost is the location of this charge inside. That information is lost. From the field outside, you can't tell where this guy is. Yeah, but that's just an aside. Did I say something? All right. Okay, so this is the Faraday's cage. You know what a Faraday's cage does? It shields you from an external field. All right, so here is a hollow conductor. You put a charge inside, and if you put a charge inside, what is it that you want? You want the field to be 0 everywhere here. So what happens is you get a bunch of positive charges collect here, whose magnitude is equal to that. You get a bunch of negative charges collect here. And these negative charges are symmetrically distributed such that the electric field is uniform there. Okay. And you see, this happens no matter where this charge is. So you can't peek inside the metal sphere to look at you can't tell where the charge is from the field outside. Yeah. So that information got lost. Okay, so you put a bunch of charges on a conductor, and they distribute such that the electric field is always perpendicular to the surface. If it was like that, there would be a component parallel to the surface which would move charges. So you can't have any component parallel to the surface. It has to be perpendicular to the surface. Okay? And you can use Gauss's law, draw this surface. The field inside is, so here's a cylinder that is, part of it is outside the surface, part of it is inside the surface. Inside the surface, the electric field is 0. So you can calculate, anyway, the electric field, the strength of the electric field is sigma by epsilon naught. Sigma is the charge density on the surface divided by epsilon naught. All right, so now let's see what this does for us. So that's the electric field strength. Let's say we put a bunch of charges here. What do the charges do to each other? They repel each other, and they want to be as far away from each other as possible. Okay, let's come to a sharp corner. These two guys would like to be far away, but they can't get too far because, you've hit the surface, and it takes energy to get out of the metal. So if you don't have the energy, you're stuck. So near sharp corners, the density is higher. The electric field strength is higher. Here you see, the electric field strength is higher. All right. What do you need to create a spark?
3 times 10 to the 6.
Volt per meter or newtons per coulomb. What about if you have an electric field strength of 2 volt per meter? I'm sorry? Yeah, you won't be able to make a spark. So if the electric field strength, okay, so under a thunderstorm, you had a charged cloud so the electric field strength here is the greatest. The charged cloud is inducing charges on this thing. The electric field strength here is the greatest and not here. So when lightning strikes, it strikes a sharp object. So one of your expensive possessions is your home. You don't want the lightning to strike and burn it down. So what do? Okay. So that's where the lightning will strike and conduct electricity to ground. Yeah. All right, guys. So that ends that chapter. Okay.